Hi, everybody. Welcome back to Artificial Intelligence. So we can continue search. Yesterday, we talked about uninformed search, and obviously today we're talking about informed search. Sorry. And this lecture is a little bit shorter. Also today, we just have 45 minutes lecture, and afterwards, Gerald will start with the first exercise. So we basically talk about two informed search strategies today, greedy best first search and A-star search. And for both search strategies, we need heuristic functions that we are going to address in the second half of this lecture. Everything you see today is also found in the Russell Novick book in the section solving problems by searching. And then you have to look into section 5 to 6. As always, at the beginning of the next lecture, what are the learning outcomes today? First, you will be able to describe the difference between informed and uninformed search. You can apply greedy best first search and A-star search, which are the two search techniques that we're going to learn today. You can discuss the influence of a heuristic on the search result. And you can decide whether a heuristic dominates another heuristic. We'll see what that means. And you can explain methods how to systematically obtain heuristics for search problems. So in some problems, it's very easy, like in this map of Romania problem. In other search problems, like the M8 puzzle, it's more complicated. And you can create simple heuristics to improve the performance of search problems. And we'll see that even slightly improving the heuristics will drastically reduce the number of nodes you have to visit due to the exponential complexity of the search techniques. Okay, so this was already discussed yesterday a bit. So what is the difference of uninformed and informed search? So in contrast to uninformed search, informed search now uses indications how promising a state is to reach a goal. And because of this additional information, you can find more efficiently a goal compared to uninformed search. Of course, there can always be cases where certain uninformed search technique is faster, but on average, this is not the case. Okay, and then basically the difference now is that the choice of the next node is based on something called the evaluation function f of n, which itself is based on a heuristic function h of n. And this heuristic function is something we'll have to design today. And hn is problem specific, so it depends on the problem at hand. So this is also something you should design carefully for the programming exercise when you design the motion planner for the autonomous car. And the only constraint you have is that the heuristic should be non-negative, and in the goal state, the heuristic has to be 0. That's the only constraint. And in essence, all informed search strategies are uniform cost search techniques, except that the F value instead of the path cost G is used in the priority queue. And for those who don't know what a heuristics is, just refers to the art of achieving good solutions with limited knowledge and time based on experience. So this is also something which you use in everyday life, or when you work as a computer scientist or engineer, you do not always find the optimal solution, but based on experience and knowledge that you have, you would try to find a solution very fast, which already is very good. Okay. Yeah, so the first informed search technique is greedy best first search. As the name suggests, we very greedily try to find the goal, so we always follow simply the best heuristic value. So in this case, the function f of n, which we use to evaluate the next node, is exactly the heuristic value. So now, how would this work in the Romania example? So here we need a heuristic that estimates the path to the cost to the goal. And so what we're going to use here is the straight line distance to the goal. So for each city, we know, okay, if you have a straight line between the city and the goal, what is the distance? And of course, this is always less than the real distance. And the optimal distance, of course, we have to figure out through search. But based on the straight line distance, we can figure out, for instance, that going to Dobreta maybe not very smart, because first of all, you have to travel a lot, and then the remaining straight line distance is still quite long. So now this is a really simple search technique. We start in Arad. We know the straight line distance is 366 kilometers. And then we expand and we see that out of these 3 children, CPU has the shortest straight line distance. So next we will expand CPU. And then we have 4 neighboring cities, out of which Fagaras has the shortest straight line distance. And then we're already in Bucharest. This was very easy and very fast. The only disadvantage is that the path that we found is 32 kilometers longer than the optimal path. Okay. So now we can start with the first tweetback question. Maybe we send again the tweetback link for those who don't know it yet. I mean, the thing is, the link that we have here, is this the old one or is this the current one that we use? So this, yes, we haven't, this is our fault. We haven't updated the tweetback link. So please use the link in the chat. So this is an ABC question. Here you see again the map of Romania. So we start in Iasi and we want to go to Fagaras. And now the question is, what happens next? So first, Niemt is expanded. So we first go to Niemt. Why? Because it has a shorter straight line distance compared to Vaslui. And then what happens next? So A, no further node is expanded because this is a dead end. B would be Iasis is expanded, so we go back. Afterwards, Niemt is again expanded due to the closest straight line distance. So this suggests that we switch back and forth. And what is also important to note is we're using the tree search version here, not the graph search version. So we don't store any explored sets or explored states in the explored set. And C is Iasis is expanded. And afterwards, Vaslui is expanded. So we go from Niemt to Iasis and then to Vaslui, since Niemt has already been expanded. So this would be C. So do we have already some results in the?
So around 70% chooses B, and then around 26% chooses C, and the remaining 6% chooses A.
Okay. Yeah. So yeah, B is the correct answer because we are using tree search, as most of you already figured out. We go to Niemt, and then the next node with the shortest straight line distance is the Iasi, and then Niemt again, and so on. So we flip forth and back here. Okay. So Vaslui would be, so C would have been correct if we would have used graph search. And of course, no further node is expanded, only happening if we cannot move anymore, but in this graph, we can always move and go to a next state. Okay, sorry, I've still not fully recovered. Okay, right, so greedy best first search, as I mentioned, is incomplete when not using an explored set, even on finite state spaces, as we've just seen. So this is the example that we just solved in the tweetback. So here you would flip between Niemt and Iasi all the time if you would use greedy best first search when you don't use an explored set. Okay, so today we have a few questions. So in the next tweetback question is greedy best first search optimal? So this is a yes/no question. So we already discussed this, so should be very clear the answer. Yeah, what's the result?
About 90% chooses no.
Yes, it's not, because we already had this case. So this was not the shortest path. We already found a counterexample. And the next question is, it's an A or B question. What is the time complexity of greedy best first search? B to the power of M or B to the power of D? And as a reminder, B was the branching factor, D was the depth of the shallowest node, and the maximum length of the path was M.
I'd say it's equally distributed.
Okay, so the answer is b to the power of m, because the heuristic chosen so badly that you don't find the shallowest goal, and you have a worst case behavior. So that A is correct. Okay, so let's talk about the performance. So completeness, we've seen it's only complete if we use an explored set, so if you use the graph search implementation. Optimality, we've seen in the count example, it's not optimal. It was also a tweetback question. Time complexity was also a tweetback question. It's b to the power of m, as I just explained. And space complexity is the same because we have to store all the states that we visit. That was quite easy. Here you see actually the example, again, the same example in our common road setting. And in the common road setting, interestingly, it works very well. So the heuristic that we use here is the Euclidean distance to the goal. So the same heuristic we use in the Romania example. It's just divided by the velocity of the current state. However, because we go with constant velocity in this example, it's the same as, because we always divide by the same velocity, it's the same as the Euclidean distance. So we start expanding, and then this is in the second level. And then you see that we almost have to expand nothing and very quickly find the solution. So this is actually, out of all the examples in this very simple scenario, really best first search for this particular example is best, but this doesn't have to hold in general. Okay, so the problem, of course, with greedy best first search is that it's not optimal. So we would like to fix that, and for that reason, we introduce A-star search. Just as a quick intermediate tweetback question, who has heard of A-star already? So yes, if you have heard of it, and no, if you haven't heard of it. I'm just curious.
So about 60% chooses no.
Okay, so quite a lot, few people have heard about it. So the people who already heard about it, if you have a better idea how to explain A-star search after you see the slides, then you can just contact us. Okay, so but essentially what we change is that the F value is not equal, does not equal the heuristic anymore, but it is a path cost. So it's the path cost G of n plus the heuristics H of n. So it's a very small change, which has a huge impact, as you will see. So now, as I said, F of n is G of n plus H of n. And the second thing we have to consider is that H of n has to be admissible. And that means for A-star search that it has to be an under approximation of the true costs. So if H of n is always lower than the true final costs, it's an admissible heuristics. And as a consequence, F of n never estimates the costs to the goal. And thus the algorithm then keeps searching for better solutions, and that in the end establishes the optimality. So for graph search implementations, we need a small modification. There we need consistent heuristics. What does it mean? It means that given the cost of a transition, so from n to n prime, given action A, we have that for all the nodes n and its successor n prime, it holds that the costs from where we start have to be less or equal than the cost to go from n to n prime plus the remaining costs at the node n prime. And then, of course, this you see already, this is some form of triangle inequality. And also what you see is that when this holds, then also you have an under approximation of the costs. The proof why this is more strict than the under approximation is rather simple, but nevertheless, we keep it out of the slides. Otherwise, we overwhelm you with too much information. It's not really crucial for this approach. So these 2 points I've just mentioned already. Okay, so the best way to explain this is by an example. We use, again, our Romania example. Now the F value is the cost for reaching this path, so which is already an exact cost because we just added it from the partial cost. Initially, of course, this is 0, plus the heuristic cost, which under approximates the remaining costs to the goal. So now we get new values, and you see KCBU has cost 393, or estimated costs, where 140 are the true costs from Arad, and then the 253 are the underestimated remaining costs to the goal. And you see that the value is the best for CBU, and for the other two cities, the value is higher. So what we will do next is we will expand CBU. And one thing happens now. So remember here, 393 were the costs. Now, because we always add the past cost, the partial past cost, the past costs are increasing and the remaining costs, of course, decreasing because we're reaching the goal. So now the total costs are approaching the true costs that we have in the end. So now here we have 413 and before we had 393. So the costs, these values are always increasing and stop when we are at the final node. It's slightly better than this one. And yeah, this is definitely the node with the smallest overall costs. So we expand Rimini to Vilcea. And now we go back because now Fagaras has smaller costs. And again, these costs are always increasing. Now we have 415. The next one we expand is 417. And then we're in Bucharest, which has 418. So you see the heuristics is already very good at the end. So 417, so the true costs were then just 418 in the end. And now the only node, or the next node that we would expand is Bucharest, which is the goal. And again, as we explained yesterday for uniform cost search, because there's no other node with smaller costs, we know this is the optimal solution. Okay, yeah, that's very nice. And of course, the other values we have, because they're under approximations, we know already there cannot be a better solution. Because if this would be an over approximation, so the values would be higher than the true values, there might still be a solution which is better. But because these values are all smaller, we know there exists no better solution. Okay. So essentially, the heuristic now steers us towards the goal, and A star only expands nodes in order of increasing F values, so that we have this F contour. So if you've seen, the F values were increasing step by step, but they were always targeted towards the goal because of this heuristic. So each contour includes nodes with F values less or equal than the I's contour, and these contours, the values of the contours are increasing from step I to step I plus 1. So this is what you see here. So we started with 380, then we had a 400 contour and then a 420 contour. And you see how these contours expand naturally in the direction of the goal. And also you see that we don't expand many other nodes because they're outside these contours, which we then call pruning the search tree, because we know that we will never have to execute or expand other nodes. Okay. So the next quick feedback question, given the optimal cost C star, does A star expand nodes where f of n is greater or equal than C star? This should also be an easy question now because we discussed this just 2 minutes ago.
So around 80% chooses no.
Yes, that's correct. So we've seen already when we are at the goal, we can stop the search because this is the optimal solution. So we will not expand any nodes which have greater values. So now let's talk again a little bit about this pruning that I already mentioned. So given the optimal cost C star, only paths with costs less or equal than C star expanded. So as a consequence, A star never expands nodes where f of n is greater than C. That was the tweetback question. So as an example, Timisoara is not expanded in the previous example. So this here T, where T, you can see the T, this is Timisoara. So we say that the subtree below Timisoara is pruned, as I already mentioned. And this concept of pruning is used a lot in AI because it, of course, brings enormous time and space savings. So we will not only use this concept today, but also in the next lecture when we talk about constraint satisfaction problems. So let's talk about the performance of A-star search. Again, we will use the branching factor B, the depth D, and the maximum length M of any path. And deriving the space and time complexity is quite involved in A-star. So we will not discuss this in detail. This is really a longer proof. So I will just present you the result in terms of the relative error, which is epsilon, and epsilon is defined as the optimal H, so the optimal heuristics minus H divided by the optimal heuristics. And the optimal heuristic, of course, are the actual costs. So when the heuristic is very close to the optimal cost, this epsilon value will approach 0. So completeness. Of course, because it's an optimal algorithm, it also has to be complete if the costs are greater than 0, which is, of course, the case. Otherwise, you don't find any meaningful result. And it's optimal. We've designed it that way, of course, only if the costs are positive. And of course, if the heuristic is admissible for tree search and consistent for graph search, but otherwise it wouldn't be an A-star search algorithm if this wouldn't be fulfilled. And time complexity is B to the power of epsilon times D. So as I've mentioned, if epsilon approaches 0, then we have a very good heuristic. If epsilon actually approaches 0, then the complexity, or epsilon is 0, let's say epsilon is exactly 0, then the complexity would be to the power of 0, which is 1. So then we would have a constant complexity. So what does that mean? If our heuristic exactly matches the true costs, how would the search be conducted then? Or what would happen if you start the search? So you can just type in the chat if you like. Yeah, we directly go to the goal. There's no backtracking. So what happens is that if the heuristic would be optimal, we would just follow each node, like we would go Arad, Sibiu, Rimnesto, Vilcea, Pitesti, Bucharest. We would not have backtracked to Fagaras. We always find in one shot the optimal path. And space complexity is the same, since all nodes are stored. Even though if you would use the tree search version, and why is that? It's because we have to store the F values for each node, and that's why even a tree search algorithm wouldn't make any sense anyways, because the only reason why you would use tree search is you don't have to store as many nodes, but because you have to know the F values anyways, this doesn't make sense for A-star search. So how would we perform for the convert example? You can see here that we initially find a solution and then we continue the search because there might be a better optimal solution, but in the end, this is again the optimal solution, exactly as for the greedy best first search technique. Although here in this situation, we have to expand more nodes, but then we are sure that this is actually optimal. In very high dimensional spaces, A-star is really very powerful because you get a very good direction towards the goal. Okay. So of course, you've seen that we have this exponential complexity when we use A-star search due to the huge space consumption of A-star search. And there are some ideas how we can alleviate this. So one idea is to use iterative deepening A-star. It's actually iterative deepening search, which we have seen yesterday. But yesterday we deepened iteratively the search depth, and now we are iteratively increasing the F costs instead of the search depth, which for cutoff rather than depth. So this has the advantage that we have, again, this linear space complexity and that it's actually also optimal. However, we have to recompute the search over and over again, as we've seen in iterative deepening yesterday. One more thing, if you already downloaded the slides yesterday, today I've I've improved the description of iterative deepening A star, because before it was not that well described. It was longer and didn't describe so well what happens. Okay. Now another approach is recursive best first search. This is also in the AI book. It's not so easy to explain with text, but a simple kind of description would be as follows. It is a simple recursive algorithm with linear space complexity, also like in iterative deepening A star, and the structure is similar to the recursive depth first search that we've seen yesterday, but it keeps track of the F value of the best alternative path. And how this is done, if you're really interested, it's in the AI book, but to be honest, it's not relevant for the exam. So if it's just for those who are really interested in that. And then there's another idea, is to just bound the memory. So maybe I remove this again. So let's say you run out of memory. So which nodes would you remove from your frontier and your explored set? Maybe you can type this in the chat. Right, so we remove the ones with the highest cost. That's a good idea. It's just like A star. Until the memory is full, the algorithms drop less promising paths to free memory, and these are the ones with higher F values. Okay, good. So that's it. So we already discussed the two informed search techniques that I wanted to discuss today. And as you've seen, if you would have a perfect heuristic, we would directly find the best path. So this I think already shows the importance of a good heuristic. And if you looked at the map of Romania, then the straight line distance kind of makes sense, and you can easily come up with this idea. However, with the 8 puzzle, it's much more tricky. So how do you find an under approximation of the costs to get from this state to this goal state? Does anybody have an idea what we can do? One more thing. Somebody asked, but memory bound is no longer necessarily optimal. Yes, that's correct. So the memory bounded A star search is not doesn't provide the optimal solution. However, the iterative deepening A star search provides the optimal solution. That's a good comment from that I've just received.
Also, one other comment quickly. So some people again said that if we could slow down the slide speed a bit.
Okay, right. So how many tiles are in the correct position? That's correct. That was a good comment. That's a good under approximation. So in this case, almost all the tiles are not in the right position. Yes. So here the under approximation of the cost would be 8. And the other one is the sum of distances to the correct square for every number. That's another one that's very good. So let's say for the tile 1, you have to move 1, 2 up and 1 to the sides. That's 3. For tile number 2, you have to go 1 to the side. That's 1, and so on. And then you add these costs just to move these tiles around, and you assume here that you can fly over the other tiles. Then you would also get an under approximation. So these are exactly the two candidates we want to discuss. So first, the number of misplaced tiles. Why is it admissible? Of course, a misplaced tile has to be moved at least once. And the other heuristics, H2, is the sum of the horizontal and vertical distances to the goal. Why is it admissible? We have to move it at least there, and we assume that we can fly over the other tiles. So again, this is an under approximation. So for tile 1, you have, as I just already explained, 3 movements. For tile 2, 1 movement. Maybe we can do tile 3. Tile 3 is here and has to go here. So we move 1 left and 1 up. So these are 2 movements we need. And if you sum them up, you have a cost of 18. So this is, of course, a more accurate heuristic. So here you have cost of 18. For the first heuristic, you have a cost of 8. And the true cost in this case is 26. So 18 is already quite good. So now there is a measure which is called the effective branching factor, which tells you how good a heuristic is. So what is the effective branching factor? So let's I can quickly draw this. Wait a second. On my whiteboard. So let's say you have a search tree that looks like this. You have a root, and then you have something like this. So you get a lot of children. And then what you do is you count the number of nodes you've expanded. So here this would be 3, and this 1, 2, 3, 4, 5, 6. This would be 6. So in total 9 nodes. And you want to know how many nodes on average do I have to expand to get the exact same number of nodes on average. So it's not a straight true number. So if you would have a branching factor, let's say of 2, and the branching factor here means that for each node has the same number of children. Then we would have 2 and 4, it would be 6. So it's a little bit more. If we would have a branching factor of 3, then we would have 3 here and 9 here. So then we would have in total 12. So it's between 2 and 3 is the branching factors. Maybe something like 2.5 would be this average branching factor. So of course, in reality, you always have a different number of children, but we want to count the number of all children and want to have an average branching factor, which gives us an idea how many children we have to expand for each node on average. Okay, yeah, that's what it does. So let's look at an example. Or let's look at first at the formula. So we have n plus 1 is the number of nodes plus 1 because you start with the root, and that matches 1 plus b star nodes in the first level, then b star squared nodes in the second level, and so on up to b star to the power of d. So if a star would generate a solution at depth 5 using 52 nodes, then you have to find this average branching factor through iteration, such that if you insert this value, you roughly get the number of nodes. So here it's n plus 1. So 53 is approximately this value. So then the average branching factor is 1.92. And this makes it possible to compare heuristics applied to problems of different size. And why? Of course, because if you have an average branching factor, then of course you have whether you have a depth of 5 or 10, then on average you usually expand the same number of nodes, and then you can compare, for instance, the performance of the heuristic for a problem which you find at depth 5 with a problem where you find a goal at depth 10, and yeah, this makes it easy to evaluate the performance of a heuristic. So let's look at the example of we have computed the solutions of the 8 puzzle for 100 random scenarios. So we have 100 random initial states. And then if you look at iterative deepening search for search depths of 2, on average, we required 10 nodes. For search depths of 4, we have 112 nodes and so on. And for depths of 12, we already have more than 3 million nodes. So we cannot continue beyond that because we're running out of memory. If you use A star with heuristic 1 that one of you already suggested today, we can go beyond these depths and even compute solutions with a solution depth of 24. If you use the even better heuristics that also was proposed today, then you see at the beginning there's not much difference. But if you look at depth 24, we can reduce the number of nodes from 39,000 to roughly 1,600. And now let's look at the effective branching factor. So the iterative deepening search has a roughly an average branching factor of 2.7, 2.8. And you can see that this branching factor is quite constant over the depths of the shallowest node. So of the over basically the complexity of the search problem. And a star search with heuristic 1 has roughly an average branching factor of 1.45. And if you have the better heuristics, then the branching factor improves to roughly 1.26 to 7, something like that. So that's not a huge difference, but because of the exponential complexity, you see that in the end, the number of nodes that you need is drastically reduced. Okay, today we have many tweetback questions. The next tweetback question is H2 always better or equally as H1? So as a reminder, H1 is the number of misplaced tiles, and H2 is the sum of the distances to the goal position using horizontal and vertical movements.
So about 65% chooses yes.
Okay, yeah, and that's the correct answer. It's strictly better. How can we say that a heuristic is strictly better than another heuristic? So this we already answered through feedback. The reason is that for every node, we have that the heuristic H2 is greater or equal than a heuristic H1. So then we can say that H2 dominates H1. And what happens is that you strictly expand less nodes. As we already have seen, A star using heuristic H2 will never expand more nodes than with H2 because of the following reason. You only expand nodes where f of n is less than the optimal cost C star. So now if you replace f of n with h of n plus g of n and put g of n to the other side of the inequality, then you have the inequality that tells you that you only expand nodes n for which h of n is less than c star minus gn. So c star minus gn, this is fixed. This is a fixed constant. And h of n, of course, can be influenced. So if h of n is higher, this inequality is fulfilled for fewer nodes n. And that's why H2 is always greater than H1. It means this inequality is fulfilled strictly only for less n's than in the other case. So this is, we can really say this is always better. Okay. Now let's talk about another option of finding a heuristic. Oh, no, sorry. So what we have seen, sorry, I was one slide ahead. So we have now come up with these heuristics H1 and H2. And the question now is there a way how we can systematically obtain these heuristics? In some cases, it might be really hard to find a good heuristic. And the idea is to come up with relaxed problems. So just imagine you're driving a car and all of a sudden the mayor of the city tells you, because you're such a good person, you are the only person who doesn't have to respect traffic rules. That means you can go through the red traffic light, you can overspeed, you can do anything you want. And because of that, obviously, you can get faster to your goal. So the costs are reduced. Let's say if cost would be time to the goal, this cost would be reduced. So by removing constraints, you always have a better performance. This is, of course, a egocentric view. So if in a society you have no rules and everybody tries to benefit as much as possible individually, then the overall performance of a society would not be good. So that doesn't mean that rules are bad. It's just, if you look from a pure theoretical point of view, then removing constraints is always good for you. So what we will do, we will formalize the same problem without restrictions. And why this is always a under approximation, I've tried to explain this using this driving example, but you can also visualize this theoretically. So if you have a graph which shows you the actions that are possible with constraints, and then you remove constraints, so then certain new options are possible. So yeah, this can be really anything. Let's say if you don't have to pay tax, then you have more money and you can reach certain goals faster. But as I said, this is an ecocentric view, and as a whole society, this would not be optimal. So because of these additional nodes, you can then find a solution that is potentially has lower costs. And that's how we then obtain this under approximation. Okay. So if you look at the 8 puzzle problem, so you cannot just move from square A to B. You have to have 2 constraints fulfilled, right? Phi1 and Phi2, where Phi1 is the next position has to be blank, and the next position has to be an adjacent position. These are the 2 constraints. So now we can just remove constraints. So we can say, okay, let's remove Phi1, B is blank. So which heuristic would be obtained? We have seen this heuristic already today. If we remove the constraint that the next tile is, or the next spot has to be blank. Yes, then we obtain H2, correct. Somebody also said, can we combine H2 and H1? We can also do that. Maybe because I just received this question, does anybody have an idea how we can combine H1 and H2? We can use weights. That's correct, but there's even a better solution than computing the average. Yes, we can use the maximum. Because both are under approximations, we can use the maximum. With H1 and H2, however, it doesn't really help because H2 dominates H1, meaning that for any node, H2 is better. So if we always take the maximum of H1 and H2, we would always choose the value of H2. However, there are other heuristics. Let's say we find a heuristic H3, and H3 is in some cases better than H2, and in other cases, it's the other way around. Then computing the maximum would make a lot of sense. Okay, so if we remove H1, then a tile can move from square A to B if A is adjacent to B, which results in heuristic H2. If we remove H2, then a tile can move from square A to B if B is blank. It doesn't even have to be adjacent. And if we remove both, you can move arbitrarily from one place to another, even if that other place is not blank. And that actually leads to heuristic H1. So from the first relaxed problem, we generate H2, and from the third relaxed problem, we can derive H1. And as I mentioned already, if one is not sure which heuristic is better, we can always compute the maximum. And that is then a super heuristic because each one is an under approximation. If you compute the maximum of many under approximations, it will still be an under approximation. But always the best solution, obviously. Okay, so there's one more technique that we can use, and that is that we solve a problem just partially. And this partial solution then can be stored in a pattern database, and that also provides us with an under approximation. So there's some text now, but the easiest way is to explain it based on this example. So let's say we don't want to solve the complete 8 puzzle problem, but we just want to get the first 4 tiles in order. So tile 1, 2, 3, and 4. And the other tiles can be arbitrarily placed. They don't have to be in order. And of course, if you now run, let's say, a star search with a not so good heuristic, then you can find the exact cost that you would need to bring these 4 tiles in order. And this cost then is an under approximation of the true cost of bringing everything in order. So every time you see this pattern where there's something here, something here, something here, something here, and something here, and these tiles are ordered like this, then you can use this heuristic, which we obtained in a previous search problem. And of course, because this is a smaller search problem, this might be a search problem that is feasible, where we don't run out of memory. So we solve a lot of patterns. And then when we run the real problem, we already have very good heuristics because they are based on true subproblems. Okay. So to sum up, informed search methods require a heuristic function that estimates the cost h of n from a goal node n to the goal. So for greedy best first search, we just use h of n, and for A* search, we used h of n plus g of n. Right, and if h of n is chosen in an under-approximative way, A* search, this is of course a requirement for A* search, and then A* search always finds the optimal solution. And as we've seen, there are 2 ways to automatically, or in a, let's say in a constructive way, find these heuristics. One was to use this pattern databases, and the other one was to create problems where we remove constraints. So these were these relaxed problems and these pattern databases. Good. So now we're exactly at the end of the lecture. I hope you enjoyed the lecture so far. I'm now leaving, and then Gerald will take over with the first exercise. And I wish you a nice weekend and hope to see you again next week. Next week, we'll start with constraint solving, which is also a very interesting topic, which is still related to search problems, but it's a specialized type of search problem. And after that, we start a completely new topic, which will be logics, where you will be able to create new knowledge and use knowledge, and to prove that certain statements are correct or incorrect. The exercise will also be recorded, and
yeah, then we will have a, I would say, 5-minute break, and we continue in 5 minutes again.
Okay.
Everything is set up.
Okay. Bye.
Bye-bye. Okay, perfect. So 1 second. Okay, good. Then let's start. So hi from my side. So welcome to the first exercise session for techniques for or basics of artificial intelligence, or the lecture Grundlagen der künstlichen Intelligenz. So basically this is the first exercise we'll have for the lecture, introductory lecture, which was on intelligent agents. And now, because some people asked in the chat regarding the slides and the exercise problem statement, so the way we'll do it is we'll always upload the exercise sheets with the problems a week ahead on Moodle, so you actually have access to them already. You will find them under Lecture 2, Intelligent Agents, and we'll upload the solutions as well as the slides that I'm showing right now. So I might have some annotations and stuff in them after the exercise always. So they'll be uploaded by this evening sometime, I guess. Yeah, so far the organizational things, maybe just a couple of words about myself. So yeah, my name is Gerald. I'm a PhD candidate at Professor Althoff's group since approximately a year. And in my work, I'm basically working on safe motion planning for autonomous vehicles. And I will be doing the first 3 exercise sessions. So basically the introductory exercise that we have today, then the search part and the constraint satisfaction part. And after that, my colleague, Adrian, will take over for logic. All right, then let's just go over some quick organizational things. So most of it we've covered already, actually. So date and time of the exercise is basically always Fridays, what we have now. It might be the case that we switch a lecture with an exercise, but we'll notify you about that on time on Moodle. That always depends on the progress, how fast we are in the lecture and how fast we are in the exercise sessions. So it'll always be virtual on Zoom, as we are doing it right now, and recorded, obviously. exercise sheets and solutions. As I said previously, we always upload them to Moodle, and you'll find them a week ahead, the problems, and afterwards you'll find the solutions after the exercise. For questions, you can use the tweetback link that I think Dawi has posted in the chat already. So there'll always be a separate tweetback link for the exercise sessions. I'll try to look at some of the tweetback questions. I can't guarantee, unfortunately, that I'll answer all of them because it's a bit hard to do the exercise and at the same time answer the questions, but I'll do my best. And if there are some questions that are unanswered, then you can use the Moodle forum, and latest there you should get an answer. And additionally, I'd also just like to remind you about the tutor hour, because there were also some students asking questions. It's every Friday from 10 to 12 a.m. also in Zoom. The Zoom link is separately also posted in Moodle. And yes, you can use the tutor hour as an additional offer, basically for any questions you might have regarding lecture, exercise, exam, and so on. Okay, good. Then let's start. So before we start with discussing some of the problems of the exercise sheets, I'd just like to do a short recap and revise or summarize some of the basic concepts we need from the lecture last week. And one of those is basically the concept of rational agents. So this is one of the central aspects that we are looking at here in this whole lecture. And that's why it's also important to understand the notion of rational agents. And in this lecture, we use this definition, which is basically also shown in the lecture and which is taken from the Artificial Intelligence, a Modern Approach book. And this definition basically says for each possible percept sequence, a rational agent should select an action that is expected to maximize its performance measure given the prior percept sequence and its built-in knowledge. And now when we look at this definition, there are basically four key components that are important and which define rationality as we define it or as we need it when we are speaking about rational agents in the context of artificial intelligence. So one of them is the performance measure, obviously. So a rational agent should have some kind of performance measure which it is expected to maximize. Then we need the agent, or the rational agent has some kind of prior knowledge about the environment. So this is basically what does the agent know already about the environment it is in, about the task environment. Also, the agent has some kind of set of possible actions. So it should select an action. So selecting an action means we already have a set of possible actions which the agent already has, and which a rational agent should always, or which basically are predefined for a rational agent. And finally, what's also important is this part, so the prior percept sequence, which basically means that we have some kind of percept sequence, so some kind of sequence of observations that the agent has done in the environment up to the current time or up to now, where we want to select an action based on that. Now, when talking about rational agents, one thing that's very crucial basically in designing an intelligent agent is to understand the task environment, right? So we have to understand what is our environment, which the agent is basically perceiving and acting upon. And in the lecture, what we did is we defined some kind of categories to characterize a task environment. And I just posted 4 of those here. So in the lecture, I think it was 7 to 8. So it's just the most important ones that we're going to need for the exercise today. One of them is basically observability. So we can have fully observable or partially observable environments. Environments can be, for example, deterministic or stochastic. They can be single agent environments or environments where multiple agents are active. So then in this case, we could have a multi-agent environment. They can be static or dynamic, for example. And then there were like 3 or 4 more categories that we had, which would define the task environment for the agent. Apart from the task environment, what's also important is to categorize the agent itself. So we also learned in the lecture that agents can basically be categorized into 4 categories, and each category from top to bottom basically increases the complexity of the agent and at the same time also increases the generality. So it's more generalizable to different settings and different use cases. And here, basically, I just listed the 4 types of agents or 4 categories of agents, and one key component basically summarized in one sentence. So the details you can find in the lecture slides. A simple reflex agent, for example, is the most basic form of agent. What we do is basically the actions are just based on the current perception. Then a model-based reflex agent is an extension of that. So the problem with simple reflex agents is if the environment is just partially observable, then simple reflex agents don't perform very well. Or basically they can't handle that at all. And model-based reflex agents, they handle partial observability by introducing a so-called world model. And this world model does some kind of estimation of the environment. So we estimate the stuff in the environment that we cannot observe. Then a further extension of that are goal-based agents. So instead of a model-based reflex agent, which just chooses an action based on what it currently observes, we additionally introduce a goal. So we say the agent should keep track of a goal that it's trying to achieve, and we choose the actions according to, once, what we observe in the environment, and second of all, we choose the action according to how to achieve this goal that we have predefined, basically. And then the last extension of that are utility-based agents. So utility-based agents also try to achieve a goal, but at the same time, they try to maximize a so-called expected utility. Now, what is this utility? This utility is kind of like a higher aspect of a goal. You could translate it, or you could think of it as usefulness of the action in German. So for the German speakers, one would say Nutzen maybe. And this usefulness is basically more or less based on the performance measure we give the agent. So you can think of it this way: if you have a goal and there are multiple ways to get to the goal and multiple actions the agent can take to get to the goal, it chooses the one that maximizes the expected utility, or it should choose the one that maximizes the expected utility. Okay, good. Yeah, then this was just a quick revision and summary of some of the important stuff in the lecture that we're going to need. And then we're going to start with the first question. So this first question is going to be pretty fast, actually. I don't think I have to discuss it much because we actually went through this already. So the question is, which actions does a rational agent select? Essentially, we discussed this in the lecture already, and we just had it 3 slides before. So it's basically the definition that I showed you earlier that we're going to use in this lecture always. If a rational agent selects an action that is expected to maximize the performance measure given a prior percept sequence and the built-in knowledge. So that's basically it, the 3 key components. Obviously, selecting an action, so 4 key components that I showed you earlier, which basically define rationality in the context of rational agents. Okay, then yeah, this we could go through pretty quick, I think, because this was more or less discussed already. So the next question would be, this would be a tweetback question now. So Dawi, maybe you could post a link in the chat again so everybody can open tweetback. And then you could choose you could answer this question. So the question is, which of these games would a rational agent always win or draw at? And is it physically possible to construct such an agent at all? So yes would mean the rational agent would always win or draw. No, the rational agent might lose. And Dawi, you could start the tweetback poll already, or I don't know if it's done already. You can maybe say
it started already.
Okay, it started already. Okay, very good.
So for now, about 90% chooses no.
Okay, perfect. Yeah, that's very good. That's also the correct answer. So essentially, no, a rational agent would not always win or draw at playing poker. Why? Because the environment is only partially observable. So obviously we can just see our own cards when playing poker and not the opponent's cards. It's also highly stochastic, the environment. So in this case, we cannot guarantee that a rational agent would always win or draw at a game of poker. All right, then next question would be the same thing. So would a rational agent always win at a game of tic-tac-toe? So tic-tac-toe is also called noughts and crosses. I'm sure everybody knows it, but I can just also draw it for you again. I think everybody knows noughts and crosses. So it's basically this game where you have 9 fields, and then you would start to, I don't know, make a cross here, then your opponent makes a cross here, then you make a cross here, he does, I don't know, something like that. And then basically you win, because you have to try to get three you have to try to get 3 same figures or 3 crosses in a row, so you would win. That's basically knots and crosses. So then again, Dawi, you could start the poll for tic-tac-toe and say if a rational, so you could vote again if a rational agent would always win, yes or no.
I started for a while, so now about 85% chooses yes.
Okay. That's also very good. Yes, that's also the correct answer. Why? Because the environment in tic-tac-toe is deterministic and fully observable. Deterministic means every action that a player takes always results in the expected outcome. So when your opponent draws a cross somewhere, then you know he's going to place a cross at this position. So there's no stochastic component in that. And it's also fully observable, so you always see what's happening in the environment. And the second thing is also that for tic-tac-toe, especially, there is an algorithm that guarantees win or draw. So this algorithm exists already. It's not too complicated, and a rational agent would just do something pretty simple. So it would just implement exactly this algorithm, which is also given here in this link. So you can check out the algorithm here. I think I also have a slide for this. Let me check. Yes, exactly. So it looks a bit complicated. We won't go through this right now, but it's basically just, if you'd like, you can take a look at it at home. So it's basically just a strategy where to plot, where to place, if you're the red player, where to place your cross every time your opponent makes his move somewhere else. So that's basically the algorithm behind it, and a rational agent would also just implement this algorithm and basically always win or draw. Okay, then last question, a little more interesting. So for chess, again, tweetback. So you can start the tweetback question again. You can vote yes or no for chess, if a rational agent would always win or draw at chess.
So about 60% people chooses yes.
Okay, all right. 60%, yeah, that's again the majority, so that's also correct. In this case, it's a little harder. So the question basically is, in theory, if a rational agent could always win or draw at the game of chess. And for chess, yes, it's correct. Why? Again, because we have the same setting as before with tic-tac-toe. So our environment is deterministic, our environment is fully observable. And that's why it's basically, in theory, the same thing like with tic-tac-toe. So we would have a possibility for a rational agent to always win or draw. However, the problem with chess is that the state space is enormous. So there's basically an estimation of how many board positions and how many possible games exist. So this is something that a rational agent would have to evaluate, and this is currently just computationally infeasible. So in this case, in chess, in theory, it's possible, but in practice, we could not implement an agent currently that could solve such a task. So that could solve, or that could always win when playing chess. All right. Good. Then we can go on to the next question, which is basically, or the next problem, which is basically going through some examples and checking out which type of agent one should use for certain use cases. So the way we'll do it is we'll pick out the first example, so the GPS route guidance system. We'll go through some performance measures for a GPS route guidance system. These are just examples, so there could be obviously more. And then we will have a vote in tweetback on the type of agent. So the vote shouldn't start yet. We first have to define the performance measures. So this is something you could write in the Zoom chat maybe. So you could just write some examples for performance measures that you can think of that would be good for a GPS route guidance system. Yes, time distance, time travel, fastest, shortest route, exactly. Time to get to goal, duration, gasoline, very good. Fastest route traffic, I also see, very good. Yeah, that's basically, yeah, out also, so toll roads, yeah, perfect. Okay, thanks. So yeah, these are basically, I think you've mentioned all of them. So it's mainly time to reach the goal, fuel consumption, avoiding some toll routes, speed limits, and traffic jams, and so on. Now, with these performance measures, you could have a look again at the tweetback poll. So we can start the tweetback poll, and you can decide between the 4 types of agents that we discussed in the beginning, and say which ones would be useful for a GPS route guidance system, or suitable for a GPS route guidance. Have you started the poll already, Dawi?
Yeah, sorry, I just started.
Okay.
So slightly more people choose this goal-based agent, around 50%, and then around 40% chooses utility-based agent. The remaining chooses model-based.
Okay, good, thank you. So the good thing is, in this case, that nobody chooses a simple reflex agent. This is the good thing. Also, nobody, or hardly anybody, chose the model-based reflex agent, which is also good. So it's basically between goal-based and utility-based agent, which I almost expected. So in this case, if you take a look at the performance measures, and if you take a look at modern GPS systems or something like Google Maps or something, we would actually need a utility-based agent. So why would we need a utility-based agent? So as I said before, a utility-based agent basically extends a goal-based agent in the fact that if we have multiple options to reach a goal, we would choose the one that maximizes some kind of utility. This utility would be given by the performance measures. And in this case, basically the main or important point is it would be that you would have to find some kind of trade-off between all those performance measures that you gave here. So if you say, okay, you want to avoid traffic jams and time to reach your goal, you want to avoid toll routes, then you have to find some kind of trade-off. It might be that you have to avoid a toll route, but it increases your time to reach the goal. So this is again a trade-off you have to do. So as I said, if there are multiple options or multiple actions that would reach the goal, a utility-based agent would be necessary to determine this trade-off, which it has to do between the different aspects that you define in your performance measures. Somebody asked about learning-based agents. So I think I didn't mention this before. So learning-based agent, we didn't discuss here now explicitly, because basically any agent, any of those 4 agent groups could be extended to a learning-based agent. And yes, also a learning-based agent could be used here. However, we mainly focus on the 4 categories here that we discussed now. So the 4 basic categories of agents. Okay, then let's continue with the next example. So again, performance measure for a kettle or a water boiler. What would it be? Yeah, temperature, time to boil, low power consumption time, energy consumption. Yes, yeah, it's basically all correct. Yes, it's basically all correct. So the way we did it here is we just said, so they're all correct answers. Basically, in this case, we just said a performance measure it's a very simple kettle if the water is boiled. So the idea of a kettle is it should boil water. And this is related to, I think, temperature or boiling temperature, what somebody said, is that in this case, we said we just want to design a very simple kettle which boils water, and we just want to check if it's able to boil the water. So, okay, then you can start the tweetback poll again. So just suggest which type of agent you would use here.
Yeah, now the majority chooses simple reflex agent.
Okay.
About 78%.
Okay, good. Very nice. That's also correct. Very good. So simple reflex agent, why do we need a simple reflex agent? Because it's basically a very simple problem. We just defined a very easy performance measure saying, is the water boiled? And a simple reflex agent would just be able to handle that. We just have to define, it basically just checks the current percept at every time. So it checks, is the water boiled at current time? If not, it performs an action, so it continues boiling. If the water is boiled already, it stops boiling. So this is a very simple logic that would be implemented in such an agent. Okay, good. Then the last example, I think we would just do without tweetback quickly. So it's this bidirectional escalator on a Munich underground. So the idea would be here that, I guess you've all used them. These are these types of escalators where you have to wait on the top if people are coming from the bottom. Sometimes it's a bit of annoying if there's a lot of if there are a lot of people. And some possible performance measures here would be, of course, this is just small number of examples. There would be more. So number of people transported in a certain amount of time, the number of direction changes in a certain amount of time, or if there are too many people waiting at the bottom, one penalizes basically the number of people waiting at the bottom. So if there's a jam of people somewhere inside the underground station, then that would also penalize it. So the type of agents, I would just, for time reasons, do it quickly here. Again, is a utility-based agent again. Why do we need a utility-based agent? Because again, we have basically all these different performance measures, and we would have to somehow find a trade-off between these different ones and try to maximize the expected performance or the expected utility. So this is again something that the utility-based agent would do in such a case, because we have there are again multiple actions it can take to reach the goal. So there's not just one action, and this trade-off is basically best done using a utility-based agent. All right, good. Then we can continue with the next question. Yeah, somebody asked examples for goal-based or learning-based agents. So we also provide the additional problems in the exercise sheets, and I think there are also examples. Yes, there are examples for goal-based agents and learning-based agents, and the solutions. So these problems won't be discussed, but the solutions will be uploaded afterwards. So you will have an explanation for, or an example for a goal-based or learning-based agent there. Okay, good. Then we will continue with the next question, which basically is the vacuum cleaner environment from the lecture slides, which we say we extend this problem. So we say basically the agent performance measures as follows. We say we give 3 points for each clean floor, sorry, and we penalize 1 point for each movement. So basically every time the agent moved from A to B, we would penalize this. And every time it cleaned, we would deduct 1 point. Every time that the agent is cleaned a room, then we would award 3 points. So this is the performance measures. And what's also important, it can only perceive the room it's currently in. So if it's an A, it can only see A, basically. So first question would be, can a simple reflex agent be rational for this environment? Second question would be, okay, what about a reflex agent with a state? So that's basically a model-based reflex agent. I think we didn't introduce this word really, but I can just write it here. So model-based. Yeah, okay, good. Then let's do the first question. So the first question is basically if a simple reflex agent can be rational for this environment. And again, I would just go through this right now. So I don't think we have the time for doing another, or actually we can do a quick tweetback poll. So maybe Dawi, you could just make a tweetback poll with yes, no. Did you create one? Okay, thank you.
Yep, just started.
All right, perfect, thanks. Okay, yeah, it's looking very nice.
Yeah,
very good.
So the majority chooses no.
Okay, perfect. So it's almost 80% to choose no, and this is also correct. So the answer is no. Why? Because first of all, we say, okay, a rational agent, we remember the definition from before, should maximize the expected performance measure given the percept sequence. So in this case, it means it should clean all the floors or all the rooms with as few moves as possible. So in this case, maximum 1. Now, what would a simple reflex agent do? A simple reflex agent would implement this algorithm. There was an algorithm, a simple algorithm on slide 13 of lecture 2, which basically was, if room is dirty, then vacuum. If room is clean, then move to the next room. This was basically the algorithm. So what it would do, since a simple reflex agent can just see, chooses the action based on what it currently sees. So it doesn't store a sequence of perceptions, so it just stores what it currently sees. And the simple reflex agent would basically start cleaning room A, then it would move to room B to clean it, but it would move back to room A to clean A, since it doesn't store the past perceptions that it has. So it doesn't remember that it has cleaned room A already. And a second option would be if the simple reflex agent would just stay stationary in the in a room once it's clean, but it would still not be able to clean all floors. So it wouldn't be able to maximize the expected performance. So in both options, either it will oscillate between floors or it would just stay stationary and not be able to clean all floors. In both cases, it won't be able to be rational for this specific environment and this specific performance measure that we have defined. Okay, now what about a reflex agent with state? Maybe Dawi, you could also create this short poll here, a quick poll on TweetDeck.
I think now almost 92% chooses yes.
Okay, that's very good. That's nice. Yes, it could be. The reason is exactly what we mentioned before. So we said the simple reflex agent just chooses an action based on the current percept, and a model-based reflex agent could store or could have this percept sequence, which is longer than just the present. So it could store basically what it has seen in the past. And so once it has cleaned room A, for example, it could realize that and not go back into room A, since it still remembers in its stored percept sequence that it has cleaned room A already. So this is basically one of the key differences that we have between a model-based reflex agent and a simple reflex agent. This also comes back again to what we mentioned in the beginning with partial observability. So in this case, again, our problem or our environment is partially observable, since we can only observe the room that we're currently in. And that's why the model-based reflex agent in this case would be the better solution given this problem, or would be the solution that would be rational in this case, given this problem given this problem statement and the performance measure. All right, then in the end, we have a kind of like a general text question. So it's basically a little bit a discussion question, and it should let you think a little about the difficulty of characterizing environments and determining whether, for example, environments are stochastic, deterministic, and so on. And that's why we have this problem where we have 3 different opinions about a game of billiards. So the first opinion is from Andrea. So she says a game of billiards is deterministic because a player's action is always determined by the state of the table and where the ball is. Then we have the opinion of Bernhard, who says a game of billiard is stochastic because one player doesn't know what the other player will do. And then we have a third opinion still of Catherine. She says a game of billiard is also stochastic because it's impossible to know exactly where the ball is and what the shape of the ball and the table are. And when the player hits the ball, it might go somewhere else than intended. Okay, so since we have a little time left, I think it would be also cool if we do a short tweetback quiz here. So in this case, it's basically a discussion question. So it would just be to get an impression of what you guys think about the different opinions, or who agrees with whom. So Daoyi, maybe you could just create a quick poll again with ABC, or Andrea, Bernhard, and Catherine, and just you could just vote who you agree with in this case. Yeah, exactly. So this would be just to get an impression of who thinks of what. Yeah.
Yeah, I think around half of the people agrees with C.
Okay, yeah, that's what I almost thought. Okay, cool. Yeah, so we can go through the different statements once. So let's start with B maybe. So because yeah, we just start with Bernhard. This is actually pretty simple, or it's a pretty important explanation here. So in this case, it depends a little what we define the other players as. So if we regard the other players as other agents, then we have a multi-agent environment, and this multi-agent environment is not necessarily stochastic. Because as we already discussed in the lecture once, we also had this example of chess. So chess, we also said, is if we have chess as a multi-agent environment, then it's deterministic. So it's not necessarily stochastic. If we, on the other hand, regard the other player as part of the environment, then the environment is stochastic, because it can basically change and you don't know exactly what's going to happen. So there's no determinism then anymore. Now to Andrea, for example, she says a game of billiard is deterministic. A player's action is determined by the state of the table and where the ball is. And this basically is a contradiction to what Catherine says. So these are a little kind of related, or because they're exactly opposite opinions, more or less. She says a game of billiard is stochastic because even if you know where the ball is and what the state of the table is, you cannot guarantee, or you cannot say exactly where it's going to end up. So when the player hits the ball, it might go somewhere else than you expect it to go. Yeah, so in this case, the thing is, and that's why I also believe that most people voted for C, is that in fact, even if, so in a perfect world where you would have a, let's say, a perfect table, a perfect ball for the billiard and a perfect cue and everything, and you hit the ball, then it might be a deterministic problem. So if you hit the ball at a certain position, at a certain angle, you could say exactly where it ends up. But in reality, you might have maybe a table which is not 100% flat. You might have balls that are a little damaged. You might have a cue which is maybe not 100% perfect, or a player which is not perfectly skilled that it hits the ball exactly there where it intends to hit the ball. So in this case, these are these stochastic components that this introduces. And that's why the idea would be, and that's why I also believe most people have voted for C, is that you would always have a stochastic component within the game of billiards. And wait, sorry, 1 second, I just looked at the, yeah. And the idea would be that if you have an agent which should be applied to the problem of billiards now, is that you would always, or currently always, try to implement this agent with some kind of stochastic environment model, right? So you would always have some kind of stochastic world model which accounts for uncertainties when you hit the ball, which would account for uncertainties within the table, and so on. And yeah, that's why I would also say probably C is the best, or the explanation that one could agree with most in this case currently, because yeah, as we said, we don't have a perfect world where everything is 100% deterministic when it comes to for example, a game of billiards. You have like maybe a ball which is not perfect, a table which is not perfect, and so on. Okay, then I think that was it, basically. Yes. So this last question was basically just a kind of like a discussion point to understand a little how difficult it's maybe to characterize task environments, and that this is actually a crucial aspect of when you want to design an intelligent agent, that you really have to define the domain that you're in and define the environment, and also define and characterize the environment correctly, and that this is sometimes maybe not so simple as it may seem in the beginning. Okay. Then I can just check. I think we have 1 minute left still. Okay, I can just check maybe some tweetback questions. Okay, somebody said, is physically speaking deterministic? Yeah, as I said, so deterministic and stochastic refers to the environment. And in the end, basically, what it means is that if you would have perfect conditions, then it would be a deterministic game, right? But we say, okay, we have these uncertainties due to certain aspects that are not perfect in the real world. And that's what we see there is this stochastic component that the ball might maybe not go 100% in this direction, or it might deviate slightly from where we expect it to go. And this is basically the stochastic environment, what we mean. Okay. Let's see. Okay, is the environment fully observable and known? I don't know to which this refers to right now. Okay. Okay. Yeah, then I think I'll try to answer some of the tweetback questions afterwards still, as long as the session is open. Yeah, the exercise basically is over now already. So if there are any questions that are unanswered or questions you have still regarding the problems, then please use the Moodle forum. As I said, due to time constraints, it's a bit hard to answer all of the questions in the chat and stuff while presenting the exercise at the same time. So you can use the tutor hours and the Moodle forum for any questions you might still have. And yeah, apart from that, I think we can close the session for today. Yes, because somebody asked the additional problems, no, they won't be discussed. We will upload the solution to those, and you can use, for example, the tutor hours if you have any questions to the additional problems, or also the Moodle forum, as I said already. Okay, good. Then I think we can finish the session for today. So thanks all for joining. Have a nice weekend, and then I'll see you next Friday in the next exercise session. All right, thank you. Bye-bye.